Hello, my name is Jack Mitchell, and this is the front of my prototype of the counting circuit. This is the back of the prototype of my counting circuit. Today, I would like to show you the steps it takes to get to the PBC counting circuit. Starting off with the button input. The button input uses a pull-up resistor. The idea of a pull-up resistor is that the NAND logic gate will receive a high status when the button is not pressed, and then inverting the output to a low, allowing for the LED to turn on because of the way it's wired. When I do press the button, the NAND logic gate then receives a low and inverts it to a high for the LED then to not turn on. And that is how the button input works. Next, we have the NAND gate oscillator. The NAND gate oscillator works by using the first part of this project, the button input. When it's pressed, the button input allows for the NAND gate outcome to change from a low to a high. This in turn allows the capacitor to charge and discharge highs and lows into the second and first NAND gates to give different digital inputs and outputs. As the capacitor changes the inputs and outputs of the NAND logic gate, the LED then produces a flickering effect, creating a clock pulse for the upcoming chips. Thirdly, we have the decade counter, and we start to see how the circuit will form into the counting circuit that I showed at the beginning. The decade counter works from the 4017 chip, and how the 4011 chip output then goes into the input of the pin 14, which then forms a clock pulse, which produces a counter that then increases the count of the 4017 chip that activates the corresponding output pins, and result the LEDs are turned on and off in order. Fourthly, we have the decimal counting binary up and down counter. This contains the 4510 chip, which displays the binary code in the LEDs. The decade counter's output works into the 4510 input to generate a clock similar to the one in the decade counter. The 4017 output divides by 10, allowing for the change in the clock's pulse to slow down. The binary code is displayed on the LEDs 1, 2, 4, 8. Each of these LEDs is doubled in length that another is able to produce 0 to 15 in binary with all these LEDs. So the first LED A1 is on for 1 second, off for another, just like the number 1 in the binary game. From there, it keeps on doubling until 8. Fifthly, we have the binary counting decimal decoder, and it works by connecting the output of the 4510 chip to the corresponding inputs of the 4511 chip. Once the 4511 inputs are connected, the processor then decodes the binary code into numbers that humans know, base 10. Sixthly, we have the 7-segment display, which works by taking the input of the binary counting decimal decoder 4511. It then goes through the corresponding resistor to the corresponding input of the 7-segment display to then display the number, which would be in base 10, 0 to 9. This is the front of my counting circuit PBC as it is soldered now. This is the back of my counting circuit PBC as it is soldered now. But how do all these steps work together to produce a counting circuit? The counting circuit works from the button input as it will allow the NAND gate oscillator to start working. The NAND gate oscillator produces a clock pulse for the whole circuit to count. After the output of the 4017 count, it allows the 4510 to decode it into binary. Then the 4511 decodes it into the 7-segment display to display it in base 10. As shown right here, it can count up and down. After you put in your counting circuit PBC into a case, you have a fully functioning counting circuit PBC. And thank you for watching my YouTube video, and I hope you have a great day.